All right, so today we're going to prove the Minkowski inequality, which states that for any x and y contained in the R to the n, the norm of x plus y is less than or equal to the norm of x plus the norm of y. And we, of course, have the definition of x dot y for any x and y contained in R to the n. And we have the definition of the norm of x for any x in R to the n. So the way we're going to start this proof, we're going to look at the norm of x plus y squared. So the norm of x plus y squared. We know, so we're going to use the definition of the norm. So this is equal to, so I'm going to put parenthesis and the square root, right? So I from 1 to n of x of I plus y sub I squared. And this whole thing is squared. Now, I know that this thing is the same thing as its absolute value, but since everything under the radical, right, is positive, then I know that this term here is the same thing as this here. And now, for each of these terms, I'm going to distribute it. So for here, this will be the sum from 1 to n of x of I squared plus 2x of I y sub I plus y sub I squared. And now I'm going to use my properties of finite sums. So this is equal to the sum from 1 to n of x of I squared plus 2 times the sum from I equals 1 to n of x of I y sub I plus the sum from I equals 1 to n of y sub I squared. Now, I want to get the norm of x squared, and I can get that using this term, right? Because this, since this is positive, I know this is equivalent to, parentheses, the square root of the sum from 1 to n of x of I squared, and I know the sum from 1 to n of x of I times y sub I, by definition, is the dot product. So I'm just going to put that there. So plus 2 times x dot y. And then I'm going to do the same thing I did with the x of i's here. Have that parenthesis, the square root, the sum from 1 to n of y sub I squared. And then this is equal to, right? We know the square root of the sum from 1 to n of x of I squared is just the norm of x. But we're going to square it because it's squared. Plus 2x dot y plus, and then this will be the norm of y squared. Now, I know that x dot y can either be positive or negative. So regardless of what we choose, if this were negative, then the absolute value of x dot y would be bigger than this, obviously, right? And if x dot y were positive, then the absolute value of x dot y would be equal to x dot y, right? The absolute value would be equal to this. So I know regardless, this here is going to be less than or equal to the norm of x squared plus 2 absolute value of x dot y plus the norm of y squared. Now, the Cauchy-Schwarz inequality, so Cauchy-Schwarz told us, so this will be squared, it told us that the absolute value of x dot y, right, is less than or equal to the norm of x times the norm of y. We know that this is less than or equal to this here. And then, of course, we have that norm of y squared. And what this is, we know this is equal to the norm of x plus the norm of y squared. So what we have, so thus we have, right, we have the norm of x plus y squared is less than or equal to the norm of x plus the norm of y squared. And of course, we can take the square root of both sides of this. Since both of them are positive, we know that this is the same thing as the absolute value of x plus, not the absolute value, the norm of x plus y is less than or equal to the norm of x plus the norm of y. And that is the Minkowski inequality. That is what we tried to prove.